Welcome back to R for Economics. In this episode, we're going to be talking about the maximum likelihood estimation. So first we need to install the package maxLik. I'm going to take a moment to do this. And then we're going to attach the library, maxLik library. And in order to make this repeatable, we're just going to set the seed. You wouldn't have to do this normally, but I'm going to do it here so that you get the same results that I do. Now we're going to define a function, which is going to take two parameters, a mean and a standard deviation, and it's going to apply this in order to get the total log likelihood. And this is something we did in the likelihood video, where we can now get that likelihood back from a random normal variable. Now, in the other video, we had to define what mu and standard deviation are. Now that from the maximum likelihood, what it's going to do from those plots that we saw previously is that it will try to maximize it and try to find the minimum, the best values of these, which maximize the likelihood that we have here. So we start with 0, 1 as if it's standard normal. And then we can run our res. So now we've got our results from our likelihood, from our start point, and we can get the summary of those. And here what we see is that it took only a few iterations and we were able to get 1.0645 and 2.00723 with standard errors and t-stats. We can also see the log likelihood is minus 214. So if we move from these values by even a small amount, we are likely to decrease this even further or make it more negative. Okay. So our estimate are those parameters, and we can actually generate the standard errors by obtaining those directly from the Hessian, which is from the likelihood function. And you can see that the items on the diagonal are the same standard errors that are in the output. Now that's well and good, but how about we look at a linear example? So we're going to have the errors be standard, will be normal, but with a variance of a half. We're going to have the regressors with a min 2 and a max 4, and this is going to be a uniform distribution. And our function that we're looking for is a constant of 3, 2 times x, and then the error term. So if we run all these, we can see from the plot that there should be a line going through these. If we wanted to put an AB line, we could. So what do we have? Well, we have one parameter, two parameters for the mean, and then we have the standard deviation of the U's. So we want to get this into error form. So we need to put this in error form, which is that this is equal to U. And this will give us our likelihood. So this will give us a probability that our error is that based on these parameters and this data. And then we're just breaking out all of the information in what we would normally use would be a d-norm. So we're just doing this individually, separately. The other benefit of this is that if you look at something like this, it's simply just a constant. So it's going to have no effect on our overall result. We could actually add it in afterwards. So what we're going to do is we're going to start with the values 0, 0. So both betas will be 0 and a standard deviation of 1. And we're going to see what we get as a result. So this is running the maximum likelihood of a simple linear regression. And if we look at the results, what do we get? We get 2.68, which is close to 3. 3 is definitely covered. 2.09, that's definitely covered by 2. Covers 2 with the standard errors. And then we have 0.44, which is fairly close to our 0.5 that was up here in the standard deviation. So we're actually fairly close to our correct model. Now, you might be saying, well, what was all this warnings that I saw here? Okay, those warnings are when it tried to do a simulation. It said, oh, well, I got negative numbers, and it's because it's trying to take the log of something which is a negative number. So it produces a null. Why would it do that? Well, it tried to value the standard deviation, which is less than 0. So that's not going to work when you try to take the log of a negative number. So this just gives you warnings, and it tries a different value. So it's not actually a fatal result. Now, how close did these estimates get to a linear model? And if we do a linear model of y and x, you can see that the estimates for beta 0 and beta 1 are nearly identical to the maximum likelihood, which would mean that the standard deviation should be the same as well. So here we've shown that the maximum likelihood is comparable to the OLS, at least for this linear model. Now, if the model is more complicated, then you're going to end up with a more complicated log likelihood function, and you could end up with a more complicated structure of the parameters. And this is the benefit of maximum likelihood, is that you can then expand upon this and use much more complicated distributions, more complicated parameter models, and more complicated functional forms. Okay, great, and we'll see you in the next video.